Hi, we're now ready to do our first reel design. And by reel, I mean truly real. We're going to size a wide flange steel shape. This will be our first real numerical sample, real problem. We've got a moment demand that you determined from your statics abilities, statics model, 250 kip foot, which is a fairly typical demand on your typical 4-beam in an office building, maybe even slightly on the heavy side. But for a secondary member, that would be about right. We're going to select that steel member out of A992 grade 50 these days. That would be what your default material is going to be for your typical steel shape, right? Remember, we're going to set this up so that the steel shape looks like an eye. It's standing that way, and that's because the IXX, the second moment of area, about the x-axis is larger than the IYY. That's why we call the x-axis the strong axis. It leads directly to ultimately both stiffer and stronger for the steel cross section, right? So let's get into it here. We've got a demand of 250 kip foot. We've got our material strength. There's our yield strength. We know that we have that factor of safety that is 1.5. And although in your study notes, you already have a lot of this math already worked out, let's go through in detail here. Let's find first our allowable stress, right? And so sigma allowable is equal to our yield stress divided by our factor of safety, and our yield stress is 50 KSI, and our factor of safety is 1.5, so that means that our allowable stress is 33.3 KSI, right? 2/3 of 50 ultimately is what that means, right? So that's that part. And then let's find out what our geometric requirement is that we're going to go into our beam tables, and particularly our wide flange steel shape beam tables, to select a W shape, right? So S required is, remember, our second moment of area divided by that distance to the outer fiber, I over C, right? And that's been tabulated for us for a lot of different cross sections, particularly steel. And remember, that's going to come out of the sigma equals my over I, and sigma max equals mc over I, or m over s, et cetera, and that all led to our S required that we were going to calculate once we set the maximum bending stress equal to the allowable stress, and then go figure out what we need for this. Then that was equal to our demand moment divided by our sigma allowable, right? And for us, then, that is 250 kip feet. Take note of the units, right? That's going to be crucial here. This will be where a lot of people make mistakes. And then divide by our allowable stress, 33.3 kips per square inch. All right, so that's the key that we have, something that we have to deal with in terms of units, right? The kips over kips will cancel out, but the feet over 1 over square inch means that we actually have feet times inches squared. That's a goofy set of units. So we want to convert this feet into inches. So of course that's 12 inches per foot, right? So now the foot dimension cancels out, and we're going to have a number here that is in terms of cubic inches. And you'll find that that number, when you calculate it out, right, 250 kip foot times 12 is 3,000 kip inches. 3,000 divided by 33.3, repeating, is going to be then 90 cubic inches. Yes, and I am looking for you to include your units all the way through the calculation. Absolutely. Right, so that's our required S. Now, if we have more than that, then the section is stronger. If we have less than that, it's not strong enough. Right, so that's when we'll now go into the tables to find a trial section. And I'm going to just go look at a W14. Now remember, that first number after the W is the approximate depth, or you might think of it as the height of the cross section, right? So it's about 14 inches in total height. We need to know which one. And so you go look up these things in a table, such as you have in Appendix E of your textbook, and you just scan through where you have the various W shapes. And you got to have one that is big enough. And so if you go look at the W14 by 53, you'll find out that it's SXX. That's the I over C. So the IXX divided by the C, right? IXX here divided by that C distance to the outer fiber from the centroid is 77.8 cubic inches. We need 90, so that's not good enough. So if you go one row up, you'll find you have a W14 by 68, and its SXX is equal to 103 cubic inches, right? So that one works. Now the ones above it in the table will have even larger SXXs. So why don't we use that? I mean, great, you get more strength out of the thing. Well, it's also going to be heavier. Remember, the way we know how heavy it is by this second number. That in the W series, the first one is the approximate depth or height of the cross section. The second number is approximately how much that cross section will weigh per foot of the beam. Right, so 68 is heavier than 53. More volume would mean typically, of course, greater cost. The only thing that disrupts that is of course the volume that is produced. So the more it's produced, the more commonly people want it. That price will maybe be a little bit less because of that greater volume. The steel manufacturers are willing to take a smaller profit margin on that because of the volume that they can get by selling that. But for this class, you would typically just think about in terms of the lightest weight for now. And so I would choose then the 14 by 68. What you're going to do in the next step is to actually go choose a different W shape, a different size that will also work. And that'll be a part of a quiz.